Welcome to the session 3 on laser basics. In this session, these are the objectives. We will learn what are the essential components of a laser, then we will develop the laser theory, and when we develop the laser theory, we will learn what are Einstein's coefficients. So in the previous session, I explained how a laser works. So in that description, you might have probably identified that there are three components of a laser. The first one is the active medium. That is the material using which we make the laser. Then second one is the pumping source. It is the source of energy that we use in order to create population inversion. And the third one is the optical resonator, which is a pair of mirror between which we keep the active medium. So this is the description of an active medium. It is a material used for the construction of the laser. It can be a solid, liquid or gas. The role of the active medium is the molecules, atoms or ions in the active medium will provide suitable energy levels for excitation and de-excitation, which will lead to laser action. So that is shown here in the rectangle which contains blue spheres. That is the active medium and the atoms or molecules or ions of the active medium, and that is kept between two mirrors, M1 and M2. So those two mirrors will act as the optical resonator, and then the blue solid arrow which is shown upward, that is the indication of pumping energy or the pumping source. So the role of the optical resonator is to send a portion of the output of the laser back into the active medium in order to generate more and more stimulated emission. So the three components of the lasers you can see here: the active medium, the pumping source and the optical resonator. Pumping source, this is the description of the pumping source. In order to have laser action, it is a mandatory requirement that there should be population inversion. That means the upper energy level should be more populated than the lower energy level, and for this the atoms from the lower laser level should be taken to the upper laser level, for which energy is required, and the pumping source will provide energy in a suitable form. Optical resonator is a pair of mirrors between which we keep the active medium, and one of those mirrors will be fully reflecting and the other one is partially reflecting. As the photons build up inside the active medium, they propagate towards these mirrors and will get reflected back into the active medium, and this will further increase stimulated emission. The small amount of transmitted intensity from the second mirror is taken as the output of the laser. Now we will proceed to develop the laser theory, for which we consider a pair of energy levels E1 and E2. E1 is the lower laser level and E2 is the upper laser level, and the populations in these levels are represented by N1 and N2. Population is the number of atoms per unit volume having energy corresponding to a particular level. Now three processes which we earlier discussed are shown once more here, because the objective of developing the laser theory is to find out the rate of transition between these two levels. So there are three possible transitions. They are shown here. The first one is absorption. So when an incoming photon of energy h nu, which is equal to E2 minus E1, when that photon interacts with an atom in the ground state or an atom in the lower laser level, that atom will absorb the energy of the photon and it will be going to the energy level E2. So that process is called absorption, and the probability for this process is indicated using the coefficient B12, where B stands for the probability of a stimulated process, which means a process which is taking place in the presence of radiation, and 12 stands for the transition from level 1 to 2. Now the second one is spontaneous emission, an atom in the upper energy level will spontaneously de-excite without any triggering photon, and it will come down to the lower energy level and an emittent photon of energy equal to h nu, and the probability for this transition is given by A21, where A stands for the coefficient for spontaneous process, a process which takes place without the presence of photon, and 21 means that it is a transition from level 2 to level 1. And the third one is stimulated emission. An atom in the excited state will de-excite when an incoming photon of energy h nu interacts with that atom, or this photon will stimulate this atom to de-excite, and in that process this photon is not absorbed, unlike in the case of absorption. So this photon and the photon after the stimulated emission both will be appearing, and these two photons will be exactly identical. So we had one photon to initiate to before stimulated emission process, and after the stimulated emission process we have got two identical photons. Now in the case of laser theory, what we have to do is we will have to find out how all these transitions like absorption, spontaneous emission and stimulated emission, we will have to set up equations for the rates of all these transitions, and we will have to find out the values of these coefficients A and B when the system is in equilibrium. When a system is in equilibrium, it means there is no change in population in any level. So that means when there is an upward transition, there will be an equal number of downward transition. That means an atom which is absorbed, that will result in reduction in population in the lower level. But if the system is in equilibrium, there will be an equal number of de-excitation which will maintain the population in the lower level constant. So when the system is in equilibrium, there is no change in population in any level. So under that situation we will consider the rates of transition between all these levels and get equations for A coefficient and B coefficient. So in the previous session I explained how a laser works. So in that description you might have probably identified that there are three components of a laser. The first one is the active medium, that is the material using which we make the laser. Then second one is the pumping source, it is the source of energy that we use in order to create population inversion. And the third one is the optical resonator, which is a pair of mirror between which we keep the active medium. So the rate of absorption is given by the equation 1, RAB equal to B1 to N1 rho. Similarly, we can write down the rate of spontaneous emission. Spontaneous emission is the transition from 2 to 1, level 2 to 1, and it does not require a photon, so it is dependent only on the population in the upper level from which the de-excitation will take place. So we write down the equation for spontaneous emission like this: RSP equal to A21 N2, where A21 is the coefficient related to spontaneous emission, N2 is the population in the level 2, and the last one is stimulated emission. It is written similar to equation 1, but only thing is that it is a transition from 2 to 1, so it depends on the population in the level 2. So RST is equal to B21 N2 rho. So these are the three equations with which we will start to develop the laser theory. So we have got three type of transition between the levels E1 and E2. But when the system is in equilibrium at a given temperature, which we term the thermal equilibrium. So whenever a system is in thermal equilibrium, the population in any level will not change. So that principle is called the principle of detailed balance. So that means whatever be the number of transitions, for example in the upward direction, that will be compensated by an equal number of downward transitions. So whichever atoms which are lost from a particular level will be compensated by another transition of equal number, and that will result in a constant population in all the levels. So when we consider the principle of detailed balance, we can write down the equation like this: the total number of upward transition equal to the total number of downward transition. So that means total number of absorption is equal to the sum of spontaneous emission and stimulated emission. So from that equation, if you rewrite that equation, you will be able to write down an equation for rho nu, which is the number of photons per unit volume of frequency nu. So that can be written using this equation: A21 N2 divided by B12 N1 minus B21 N2. So in that equation we will make a small modification in order to make use of the Boltzmann's equation, from which we will know what is the ratio between N1 and N2. So we just want to rewrite this equation in terms of N1 by N2. For that we will divide all the terms in the numerator and denominator with N2. So that will give us the equation for rho nu equal to A21 divided by B12 N1 by N2 minus B21. So that is equation number 4. So in this equation now what we are going to do is, we know what is the ratio between N1 and N2 from Boltzmann distribution. If the system is in thermal equilibrium, the population at various levels will maintain a ratio, and that is what we call the Boltzmann distribution. So that is actually taken from the equation for population at each of the individual levels from the Boltzmann equation. For example, the equation can be represented like this: N1 equal to a constant into exponential minus E1 by KT, where E1 is the energy level in which the population is N1, Kb is the Boltzmann constant, and T is the absolute temperature. So similar type of equation can be written for any energy level under thermal equilibrium, and that will lead to the ratio N1 by N2 equal to exponential delta E by KT, where delta E is the difference between the two energy levels E2 and E1. So E2 minus E1 is equal to h nu, and if we so that we can write N1 by N2 is equal to exponential h nu by KT. If you are writing down N2 by N1, that will be equal to exponential negative h nu by KT. So this is the Boltzmann's equation, and that is represented by equation number 5. So you can use equation 5 in equation 4, and that will give you the equation for rho is equal to A21 by B12 exponential h nu by KT minus B21. Now in this equation, this is actually rho is the number density of photon, or it is a photon flux, and the equation for photon flux is already given by Planck's law for cavity radiation, which is a well established equation in thermodynamics. So we will make use of that equation. So first next step is to write down this equation for rho similar to the equation given by Planck's law. So in Planck's law we have got something like exponential h nu by KT minus 1. So in order to make that minus 1 over here, what we are going to do is we will divide all the terms in the equation for rho which is this equation, which is written right after the equation number 5. So in that equation for rho, we will divide all the terms in the numerator and denominator with B12. So what we are left with is rho nu equal to A21 divided by B21 whole multiplied by 1 divided by B12 by B21 into exponential h nu by kt minus 1. So that is equation number 6. So now we will make use of Planck's law for rho nu, which is given by this equation 7. Rho nu is equal to 8 pi h nu cube by c cube into 1 by exponential h nu by kt minus 1. In this equation, nu is the frequency of the photon and h is the Planck's constant, c is the speed of light. So we will compare. This is the equation for rho given by Planck's law. And whereas the laser theory is a relatively new theory compared to thermodynamics. So when we develop the equation for rho using the absorption, spontaneous emission and stimulated emission concept, we obtain the equation for rho, and that rho should match with the rho given already by thermodynamics by Planck's law. So we'll compare the equations, these two equations for rho, and we will obtain an equation for the Einstein's coefficients A and B. So comparing equation 6 and 7, we know in the case of equation 6 you have got a term A21 by B21, and correspondingly we have got in Planck's law a term 8 pi h nu cube by c cube. So these two can be equated. So the first thing that we are getting is the ratio between A21 and B21 is equal to 8 pi h nu cube by c cube, and in the next term along with the exponent we have got 1 by exponential h nu by kt minus 1 in equation 7, and in the previous case we have got instead of 1 we have got b12 by b21. So we can assume that b12 by b21 is equal to 1 or b12 equal to b21. So these are the two conclusions that we are getting when we compare the equation 6 and 7. So the results are b12 equal to b21 and A21 by B21 equal to 8 by h nu cube by c cube. The meaning of these inferences is you can interpret it like this: B12 equal to B21, which means the probability of stimulated transitions, which are probability of absorption and the probability of stimulated emission, these two are the same. That means when a photon of a particular energy is traveling through a medium, it can either cause absorption from level E1 to E2, or it is equally probable that it can cause a stimulated emission from level 2 to level 1. So which of these transitions will take place, or which of these transitions will dominate, will depend on the population in the corresponding levels. For example, if N1 is more, it can cause more chance of absorption, or if N2 is more, the stimulated emission chance will be higher. And this, therefore, since these two coefficients B12 and B21, since they are equal, we will drop the suffix and we will just call it B. And the second inference that we have is A21 by B21 equal to 8 by h nu cube by c cube. So in that case also, in the denominator we will, instead of B21 we can write B, and the numerator you have got A21. It is the probability of spontaneous emission. So it is the transition which is taking place spontaneously from level 2 to 1. But we don't have a transition like A12, which is the probability of transition from level 1 to 2 without the presence of photon or spontaneous absorption. There is nothing like spontaneous absorption, because absorption will always require the presence of photon. So that means there is no meaning in keeping the suffix 21 along with A. You can drop those suffix also, and you can just write it as A. So what we have is A by B. The ratio between spontaneous emission and stimulated emission is given by 8 by h nu cube by c cube. So these are Einstein's coefficients, A and B. They are the terms which will tell you what is the probability for spontaneous emission and stimulated emission. Now we will rearrange all the available equations and obtain some more useful ratios. For example, the ratio between rate of stimulated transition to the rate of spontaneous transition, which is R21 by R, actually this is R21 stimulated to R21 spontaneous, or that is given by B21 rho nu N2 divided by A21 N2. In this equation we can cancel N2 from numerator and denominator, so that we will be left with B21 rho nu divided by A21. That is equation number 9. Now we will make use of a previous equation, which is equation number 6. So I have written that equation once more here for ease of reference. So if you examine equation number 6, we have got an equation for rho, and on the right side you have got A21 by B21. So if you take this A21 by B21 towards the left, we will be having B21 rho nu by A21, which is what we have on the right side in equation number 9. So that means we will rearrange equation 6 and write down an equation for B21 rho nu divided by A21. So that is equal to 1 by B12 by B21 exponential h nu by kt minus 1. B12 and B21 are equal, so we will delete this ratio. So we will be having B21 rho nu by A21 is equal to 1 by exponential h nu by kt minus 1. That is equation number 10. And if you compare equation 9 and 10, we have got the ratio between stimulated emission and spontaneous emission is equal to 1 by exponential h nu by kt minus 1. It is a useful equation. That is equal to B21 by A21 into rho. The difference between this ratio and the ratio which we already obtained between A and B, it is, earlier we had A by B is equal to 8 by h nu cube by c cube, whereas now we have B by A into rho. That is equal to 1 by exponential h nu by kt minus 1. So this is the ratio between the corresponding rate of transition, whereas A by B or B by A will give you the ratio between the probabilities of the transition. The rate of the transition is the number of transition per unit time per unit volume taking place when the photon flux is rho, whereas A by B is equal to 8 by h nu cube by c cube does not depend on rho, it just depends on the frequency. Okay, so this ratio is important. It is given by R1. It is rewritten as R1. R1 is equal to B21 by A21 into rho nu, which is the ratio between the rates of stimulated emission and spontaneous emission when the incoming photon flux is rho. Now we will sum up the differences between stimulated emission and spontaneous emission as given by given in the table here. Stimulated emission, an atom which is excited will go to the ground state or lower energy level when a photon of energy equal to the energy difference between the two levels will interact with the atom in the excited state. So during that interaction, the incoming photon is not absorbed, but it will just stimulate, and after stimulated emission there will be an additional photon which is exactly similar to the stimulating photon. The feature of stimulated emission is that there will be a stimulating photon, and the photons which are generated after the stimulated emission process will be having exactly the same frequency and same phase, and it will propagate in the same direction as that of the stimulating photon. So if you remember all the special features of the laser like monochromaticity, monochromaticity. Why laser light is so monochromatic is because all the photons are generated through the stimulated emission process. So all these photons will be having exactly the same energy as that of the photon which stimulates that process. So that's why laser light is so perfectly monochromatic, so highly monochromatic. And then another thing that we learned is coherence. It is having extremely high coherence. Why? It is because all the stimulated photons, all the photons which are generated through the stimulated emission process will be having exactly the same phase as that of the stimulating photon, or it will maintain the same phase relation with that of the stimulating photon. So that is the reason for the high coherence. Then another feature is low divergence or high directionality. It is because all the photons will be propagating in the same direction as that of the stimulating photon. So when all of them are propagating in the same direction, the divergence will be less. So all the photons will be hitting the same spot, making the intensity at that spot very high. So in conclusion, all the superiority or the special features of the laser are due to the stimulated emission. Now the on contrast, spontaneous emission, it can take place at any instant. It does not require a triggering photon, and therefore all the photons will be traveling in all possible directions. It is a random process, so intensity measured at a specific location will be very very less. There is no phase synchronization. Then atoms can de-excite from any upper sublevel to a lower sublevel, so they can be composed of various energies. So none of these features of the lasers will be available in a source which is generating light through spontaneous emission. So when we are dealing with laser, what is happening inside the laser is, as much as possible, spontaneous emission will be suppressed and stimulated emission will be enhanced. So that is the reason for the special features of the laser. And the second feature, all these are what I have explained just now. Then the last one, the fifth one, the rate of transition is given. This is what we developed earlier for stimulated emission and spontaneous emission. So this is how we compare these two types of emission processes, spontaneous emission and stimulated emission. To sum up session 3, what we have learned so far is we have developed the theory for laser by considering a new concept, or by introducing a new concept which is called stimulated emission. And then Einstein's A and B coefficients are related to the probabilities of spontaneous and stimulated emission, and their ratio is given by A by B equal to 8 pi h nu cube by c cube. So to coming up in session 4, we will learn how to construct two different lasers, ruby laser and helium neon laser.